Galaxies, those magnificent islands of stars, dust, and dark matter, have captivated humankind for centuries. But what if we told you that their formation holds secrets that even the most advanced telescopes have yet to uncover? At first glance, galaxies might seem like isolated marvels scattered across the cosmos. Spiral arms elegantly slashing through darkness, elliptical giants exuding stately calm, and peculiar irregular shapes hinting at cosmic collisions. Yet, there's far more. These galactic structures are not solitary. They exist within an intricate tapestry that weaves the universe together, the cosmic web. Imagine an immense network of filaments stretching across billions of light years. Clusters of galaxies are interconnected by trails of matter, their filaments crisscrossing this vast intergalactic highway, while voids, expanses of seemingly empty space, punctuate the web like silent cosmic hollows. The cosmic web raises questions of its own. Why do galaxies cluster where they do? What invisible forces guide the flow of matter across voids and filaments? Scientists have learned that these formations of the cosmos may go beyond visible matter. This is where dark matter, a mysterious entity we cannot see or touch, comes into play. Dark matter forms the scaffolding of galaxy clusters, shaping their interactions and positioning within the universe. It is unseen, unyielding, and utterly essential. But dark matter isn't the only force influencing galactic evolution. Looming at the heart of most galaxies are black holes, regions of such immense gravity that not even light can escape. Far from being passive voids, these cosmic giants shape galaxies with incredible force. Their tremendous gravitational pull dictates the orbits of nearby stars, and their high-energy bursts of radiation regulate star formation and density. Consider this paradox for a moment: creation and destruction coexisting within one entity. Now, widen the lens. Galaxies do not merely interact with their neighbors, but also collide on massive scales. These cosmic dances unfold over millions of years, sending waves of transformation rippling through their structures. When galaxies merge, bursts of star formation illuminate the intergalactic dance floor. But these spectacular events also prompt another question. How do these interactions sculpt the future of a galaxy? Do these collisions define universal fate, or are they just one chapter in a far grander narrative? Beyond the thrill of collisions, subtle, unseen forces continue to act. Structures like the cosmic web are governed, along with galaxies themselves, by dark energy, a force that drives the expansion of the universe. While its existence is certain, its nature remains elusive. Is it a property of space itself? Is it constant or variable? These unknowns knit together a picture of the cosmos that is both beautiful and deeply mysterious. And then there's the most profound question of all. Why does the universe itself exist in this form? Could other configurations have arisen? Are we merely one version of an infinite creation, with galaxies forming differently, perhaps not at all, in other realms? These are the puzzles that fuel the drive of astronomers, physicists, and cosmologists. The search for answers lies at the heart of humanity's never-ending curiosity. Each star, every orbit, every galactic spin represents a thread in the cosmic tapestry, a story billions of years in the making. And yet, as we unravel one thread, thousands more await discovery. Sit back, for today we begin peeling back the cosmic veil, step by step, exploring the forces, entities, and enigmas shaping the very galaxies that surround us. Welcome, curious minds, to the formation of galaxies. The Big Bang marks the beginning of not just space, but also time and matter as we understand them today. It is often described as the moment when an incredibly hot, dense singularity rapidly expanded, leading to the creation of the universe. This expansion, known as inflation, propelled the universe outward at an extraordinary rate. Imagine everything compressed into a point smaller than an atom. Then, in an instant, this tiny point expanded, allowing energy and matter to exist. During the first fractions of a second after the Big Bang, the universe was unimaginably hot. Temperatures were well into the billions of degrees. At these high temperatures, particles, as we know them, could not form. Instead, the universe consisted of a dense, chaotic soup of energy. It was during this early period that fundamental particles began to emerge. Photons, the particles of light, along with quarks and gluons, were present in a plasma state that filled the universe. Quarks and gluons are two essential building blocks of matter. Quarks combined in groups due to the cooling of the universe, forming particles like protons and neutrons. This change in the state of quarks is a significant milestone because, as the universe cooled further, protons and neutrons became the foundation for the formation of atoms. The state of matter at the time, known as the quark-gluon plasma, was incredibly dense and energetic. During this cooling period, quarks and gluons started to combine more permanently, forming hadrons. Among these hadrons, protons and neutrons were the most stable and essential for the next stages of the universe's evolution. This stage also saw a phenomenon known as baryogenesis. Scientists believe that during this process, an imbalance between matter and antimatter occurred. Antimatter is like the opposite version of matter, and when matter and antimatter meet, they annihilate each other. Yet, somehow, a slight excess of matter survived. Without this imbalance, our universe, stars, and planets would not exist. The cause of this imbalance remains an open question among physicists. The cooling of the universe also allowed another critical process to occur, known as Big Bang nucleosynthesis. Around a few minutes after the Big Bang, the universe's temperature had dropped enough to enable protons and neutrons to combine, forming the first light elements. Hydrogen, along with helium and trace amounts of lithium, were the results of this process. This period was vital because it created the elemental abundance that later became the building blocks for galaxies, stars, and planets. Without this step, the heavier elements that constitute much of the material we see today wouldn't have had a starting point. Following the formation of the first light elements, the universe entered a phase that led to the creation of the cosmic microwave background, or CMB. This is the afterglow of the Big Bang and serves as a snapshot of the universe when it was approximately 380,000 years old. Before this time, the universe was still too hot for neutral atoms to form, meaning light particles, or photons, could not travel freely. Photons constantly interacted with free electrons, creating a fog-like state. However, as the universe cooled further, electrons combined with protons to form neutral hydrogen atoms in a process called decoupling. For the first time, light was able to travel freely, creating the CMB. Importantly, the CMB is not uniform. Instead, it contains tiny fluctuations in density. These small variations hold critical information about the early universe and show how different regions of the universe had slightly different amounts of matter. These initial variations in density, which were quantum in origin, were amplified during the inflationary period. Quantum fluctuations, initially at a microscopic scale, were stretched to cosmic scales as the universe expanded. These tiny differences in density were critical because they signaled over dense regions, where there was more matter, and under dense regions, where there was less matter. Over time, gravity began to pull more matter into overdense regions, leading to the formation of the cosmic web. This web consists of interconnected filaments of galaxies and clusters held together by gravity. The underdense regions became vast voids in space. Early density fluctuations were, therefore, the seeds from which galaxies, stars, and other cosmic structures eventually grew. At this stage, as the universe cooled and small density variations grew under gravity, the transition from chaos to order began. Structures started to take shape. From the subatomic chaos, just a fraction of a second after the Big Bang, the universe began organizing itself on a cosmic scale. By approximately 400,000 years after the Big Bang, large-scale structures were starting to emerge. These transitions and processes are why the universe today contains vast and intricate structures like galaxies, clusters, and the cosmic web. All of these features originated from the foundational stages set by the Big Bang and the subsequent cooling and organization periods. The interplay of matter, gravity, and quantum fluctuations shape the cosmic tapestry that continues to evolve. The universe, before the first stars, was a period known as the Dark Ages, which began roughly 10 million years after the Big Bang and lasted until approximately 100 million years after this event. During this time, the universe was filled predominantly with neutral hydrogen and helium gas. Before this era, the universe had undergone the release of the cosmic microwave background approximately 380,000 years after the Big Bang. This background radiation marked the decoupling of matter and radiation, leaving the universe dark and devoid of light sources, as no stars or galaxies had formed yet. The only variations present were slight density fluctuations scattered through the universe. These fluctuations originated from quantum ripples during the inflationary epoch and essentially served as the foundational seeds for star formation. Over time, these minor density variations developed into gravitational wells, pulling gas and matter into localized regions. The birth of the first stars, known as population III stars, was initiated by the gravitational collapse of gas clouds located within these early density fluctuations. These regions, consisting of primordial gas, created pockets where gravitational forces overcame thermal pressure, enabling the gas to collapse inward. The compression of gas caused a dramatic increase in temperatures, eventually allowing nuclear fusion to commence. Population II stars were unique in their characteristics. They were extremely massive and luminous, often ranging between 10 and 1,000 times the mass of our Sun. Unlike later generations of stars, these stars were composed entirely of hydrogen and helium, with no heavier elements, as these had not yet been formed. Due to their massive sizes, these stars had very short lifespans, lasting only about 1 to 2 million years. Their lack of metal content resulted in inefficient cooling mechanisms, which caused these stars to grow significantly larger and hotter than stars formed later in the universe's history. The ultraviolet radiation emitted by these stars played a critical role in initiating the process of cosmic reionization, which gradually ended the Dark Ages and paved the way for the development of light-filled regions. The formation of protogalaxies was the next significant milestone in this early epoch of the universe. Gas within areas of slightly higher densities began pooling and cooling, forming regions that turned into protogalaxies. These structures were irregular in shape and significantly smaller in size compared to modern galaxies. Within these protogalaxies, clusters of population II stars emerged. When these massive stars eventually exploded into supernovae, they expelled materials, including metals, into their surroundings. This enrichment of surrounding gas with heavy elements allowed subsequent generations of stars, known as population II stars, to take shape. Another pivotal process in this phase was the merging of protogalaxies due to gravitational interactions. Over time, smaller protogalaxies combined to form more extensive and complex systems. This process also triggered burst phases of star formation, accelerating the transformation of the universe and leading to the creation of larger galaxies. Gravitational forces were the key mechanism responsible for the clustering of gas and the formation of the first stars and protogalaxies. Without gravity, the universe would have remained scattered, with diffuse clouds of hydrogen and helium gas distributed evenly. Early density fluctuations acted as gravitational centers or seeds, which helped draw gas clouds toward them. These regions of higher density accumulated neutral gas and provided the initial sites for star formation. Over millions of years, these pockets continued to evolve, giving rise to structured systems like protogalaxies, which later formed the foundation of larger astronomical systems. The development of the first stars and protogalaxies unfolded according to a general timeline. By around 100 million years after the Big Bang, the first dense clouds of gas had collapsed, forming population II stars. These stars began clustering into protogalaxies approximately 150 million years after the Big Bang. By the period between 300 and 500 million years after the Big Bang, protogalaxies had started merging to create larger structures. This led to the development of the first true galaxies, with advanced star-forming regions housed within these intricate systems. An important concept to note in the early development of the universe is the emergence of the cosmic web. The cosmic web is the universe's large-scale structure, which interconnects protogalaxies, stars, and gas clouds along filamentary patterns. These filaments served as the underlying framework where matter concentrated, forming star-forming regions. Light from the earliest regions illuminated this cosmic web as it began to take shape. Population II stars were critical in unveiling this structure, as their light emitted across the universe began to illuminate the intricate network of filaments and clusters, transforming previously dark regions into vibrant interconnected systems. Observational evidence has been integral in understanding the formation of the universe's first stars and protogalaxies. Modern telescopes, such as the James Webb Space Telescope, JWST, have provided glimpses of galaxies from this very early epoch, offering direct observations of structures from billions of years ago. Indirect evidence has also been significant. For example, extremely metal-poor stars, which are remnants of early star generations, serve as relics, providing clues about the characteristics of population II stars. Additionally, anisotropies in the cosmic microwave background offer valuable insights into density fluctuations from the Dark Ages, which eventually led to early star and protogalaxy formation. The legacy of the first stars and protogalaxies extends far beyond their immediate era. These stars were responsible for the initial chemical enrichment of the universe. Heavy elements like carbon, oxygen, and iron formed within population III stars were dispersed into their surroundings through supernova explosions, creating the fundamental elements necessary for planet and life formation. The merging and evolution of protogalaxies created the building blocks of modern galaxies observed today. Early stellar systems and their intense energy outputs contributed to the reionization of the universe, transitioning it from an opaque state to the light-filled universe visible now. The epoch of reionization, often considered one of the most pivotal phases in the history of the universe, marks the transition from a dark, neutral universe to one that is illuminated by the first stars and galaxies. To understand its importance, we need to explore what happened before this epoch, how it unfolded, and the physical processes that governed this transformation. The story begins approximately 300,000 years after the Big Bang, during a period we call recombination. At this time, the universe, which had expanded and cooled significantly, allowed protons and electrons to combine and form neutral hydrogen atoms. This neutral hydrogen dominated the universe, and in the absence of stars or galaxies, the universe was dark. For hundreds of millions of years, the universe remained in this state, often referred to as the cosmic dark ages. However, during this period, gravity was hard at work. Tiny density fluctuations in the primordial universe, which originated from quantum fluctuations during inflation, acted as seeds for structure formation. Gravity caused these slightly denser regions to collapse further, forming clumps of matter. Over time, these clumps grew larger and denser, eventually leading to the formation of dark matter halos. These halos acted as gravitational wells, pulling in gas and creating the conditions necessary for the formation of the first stars. By around 100 million years after the Big Bang, the first population III stars began to form within these dark matter halos. These stars, composed almost entirely of hydrogen and helium, were massive, short-lived, and intensely luminous. The formation of these stars marked the beginning of the epoch of reionization. Their high-energy ultraviolet photons began ionizing the surrounding neutral hydrogen, creating ionized bubbles. These stars lived fast and died young, ending their lives in spectacular supernova explosions that enriched their surroundings with heavier elements. This enrichment paved the way for the formation of subsequent generations of stars and the birth of the first galaxies. Approximately 500 million years after the Big Bang, reionization entered its main phase. At this point, the first galaxies had formed, hosting stars that continued to emit ionizing radiation. These galaxies, along with quasars powered by supermassive black holes, became the dominant sources of ionizing photons. The ionized bubbles around individual galaxies began to grow and merge, forming larger ionized regions. This patchy nature of reionization persisted as ionized regions expanded, leaving portions of the universe still neutral. Between 500 million and 1 billion years after the Big Bang, the universe transitioned from being partially ionized to fully ionized. The ionized bubbles coalesced, and by the end of this period, the hydrogen in the vast intergalactic medium was completely ionized. Dense regions within galaxies, however, remained neutral due to the shielding effect of gas clouds. The completion of reionization marked the end of the cosmic dark ages and the beginning of a universe fully illuminated by stars and galaxies. Reionization was driven by three primary sources. The first generation of stars, known as population II stars, played a critical role during the early stages. These stars, lacking heavier elements, were incredibly hot and emitted large amounts of ultraviolet radiation. However, due to their short lifespans, their contribution was limited to the initial phase of reionization. The formation of galaxies hosting second-generation stars took over as the principal contributors. Starburst activity in these galaxies released copious amounts of ultraviolet photons, which ionized the surrounding hydrogen. Finally, quasars, which are powered by accreting supermassive black holes, contributed significantly to reionization on larger scales. Their intense radiation ionized hydrogen far beyond the immediate vicinity of galaxies. The physics of reionization revolves around the interaction between high-energy photons and hydrogen atoms. Photons with energies above 13.6 electron volts ionize neutral hydrogen, breaking it into protons and electrons. This ionization created regions of ionized hydrogen, also known as HII regions, around ionizing sources. These ionized regions expanded as more photons were emitted. The expansion of these regions heated the intergalactic medium, increasing its temperature and pressure. This thermal impact suppressed the formation of smaller structures by preventing gas from cooling and condensing into new halos. A critical factor in determining the efficiency of reionization was the escape fraction of ionizing photons from galaxies. Dense gas clouds within galaxies could trap these photons, slowing the reionization process. The fraction of photons that successfully escaped into the intergalactic medium played a significant role in shaping the timeline and progression of reionization. Evidence for the epoch of reionization comes from several observational sources. The cosmic microwave background radiation, the afterglow of the Big Bang, holds imprints of reionization in its polarization measurements. Observations by telescopes like the Wilkinson Microwave Anisotropy Probe and the Planck satellite have provided estimates for when reionization began. Quasar absorption spectra offer another line of evidence. The presence of neutral hydrogen at high redshifts is indicated by absorption features known as Gunn-Peterson troughs. The absence of these troughs at lower redshifts suggests the universe had become fully ionized. Lyman alpha emission lines, which arise from transitions in hydrogen atoms, serve as tracers of ionized regions around galaxies and quasars. Observations of high redshift galaxies have provided insights into the sources and timing of reionization. Surveys targeting galaxies at redshifts between 6 and 10 are particularly valuable in understanding this epoch. Despite significant progress in understanding reionization, several challenges remain. One major challenge is the photon budget, which involves estimating the number of ionizing photons required to ionize the intergalactic medium. Balancing contributions from stars, galaxies, and quasars to this photon budget is a complex task. The overlapping and evolving nature of ionized bubbles adds further complexity to theoretical models. Additionally, uncertainties in the escape fraction of ionizing photons complicate efforts to accurately model the reionization process. The impact of reionization on galaxy formation was profound. As the intergalactic medium became ionized and heated, gas accretion into smaller halos was suppressed. This suppression limited star formation in these halos, while larger halos, which could withstand the increased pressure, continued forming stars and galaxies. The enrichment of the universe with heavier elements by population, II stars, and their supernova enabled the formation of subsequent generations of stars, as well as the formation of planets and complex molecules in later epochs. Reionization also influenced the large-scale structure of the universe. It played a role in defining the cosmic web, influencing the distribution of galaxies, clusters, and voids. The interplay between ionization, heating, and gravity shaped the clustering of galaxies and the emergence of large-scale structures. Modern studies and simulations provide valuable insights into the epoch of reionization. Hydrodynamic simulations, such as those conducted by Evolved Galaxy Assembly in large environments and the Illustries project, have advanced our understanding of the progression of reionization. These simulations model the growth of ionized bubbles, the feedback effects of galaxies, and the interplay between ionization and structure formation. Observational programs, including those conducted with the James Webb Space Telescope, are focusing on high redshift galaxies to probe the sources and timing of reionization. Additionally, 21-centimeter radio astronomy, which traces neutral hydrogen during reionization, is a promising avenue for mapping this epoch in detail. The epoch of reionization represents a transformative period in the history of the universe. It signifies the emergence of the first stars and galaxies, the ionization of neutral hydrogen, and the end of the cosmic dark ages. While significant strides have been made in understanding this epoch, many mysteries remain. Future observations and theoretical advancements hold the key to unraveling the remaining complexities of this remarkable era. Through continued exploration, we may gain deeper insights into the processes that shape the universe and pave the way for the cosmic landscape we observe today. Feedback mechanisms are processes where the output of a system influences its own operations. These mechanisms serve as critical tools in the regulation of various systems, including galaxies. One area where feedback mechanisms play a significant role is the control of star formation and galactic evolution. Without these mechanisms, galaxies would not be able to regulate their growth and structure efficiently. Feedback can be categorized as either positive or negative. Positive feedback enhances or accelerates a process, leading to exponential growth or increased activity, while negative feedback slows or halts processes, introducing stability and balance to the system. Galaxies depend on feedback mechanisms to prevent the overproduction of stars and maintain a balanced structure. Without feedback, galaxies would continue collapsing under their gravity and form stars uncontrollably until all gas supplies were depleted. Feedback regulates the rate of star formation, helping to prevent this unsustainable growth. It is crucial in shaping the structure and evolution of galaxies by modulating the processes that contribute to their development. Stellar feedback emerges as an essential contributor to star formation and galactic stability. Stellar winds are one of the major sources of stellar feedback and arise when stars lose mass in the form of high-speed outflows of gas. These winds exert a force on the surrounding interstellar gas, pushing it outward and heating the interstellar medium, often referred to as ISM. This process can result in the creation of hot gas bubbles around the stars. Depending on the pressure surrounding this hot gas, it can either cool and condense to form new stars or escape the galaxy altogether, depending on the interplay between gravitational and thermal forces. Stellar winds have dual impacts on star formation. On one hand, the increased thermal pressure within the interstellar medium caused by these winds can inhibit the collapse of nearby gas clouds, thereby suppressing the formation of new stars. This increased pressure prevents the required density from forming in the clouds, resulting in a phenomenon known as star formation suppression. On the other hand, in specific conditions where the gas clouds are compressed due to stellar winds, new stars may begin forming. This duality underscores the nuanced effects of feedback mechanisms. Supernova feedback, another form of stellar feedback, is highly impactful. Supernova are explosions marking the death of massive stars. When these stars explode, they release substantial amounts of energy in the form of heat, kinetic energy, radiation, and particles. These events produce supernova remnants, which are bubbles of hot, expanding gas. These remnants can shock the surrounding interstellar medium, compressing molecular gas clouds in their vicinity and triggering the formation of new stars. The energy released during a supernova heats the surrounding medium, creating turbulence and increasing the overall energy of the area. This heat can prevent gas from cooling and condensing into new stars and serves as negative feedback, thereby regulating the pace of star formation. The frequency and intensity of supernova explosions play a role in expelling gas from the galaxy, particularly in star-forming regions. Such expulsions lead to a significant drop in available material for star formation, temporarily halting the process. Supernova feedback also shapes the morphology of galaxies, influencing their classification as spiral, elliptical, or irregular in structure. Active galactic nuclei, commonly referred to as agents, are another source of feedback in the regulation of galactic growth. At the heart of galaxies lie supermassive black holes that act as the core of active galactic nuclei. When these black holes accumulate significant amounts of gas and dust, they release an immense amount of energy across the electromagnetic spectrum. The energy release from an active galactic nucleus can manifest in various forms, including powerful radio jets and energetic winds. Supermassive black holes launch radio jets that interact with the interstellar medium, heating and displacing the existing gas. These jets have the capacity to push significant amounts of gas out of a galaxy's central regions, altering the localized environment. Additionally, supermassive black holes produce winds powered by the accretion of matter around them. These winds play a similar role in expelling gas from galaxy cores, reducing the material left for star formation. X-ray emissions originating from active galactic nuclei also contribute to this regulation, as these high-energy rays heat the gas, suppressing its ability to cool and condense into new stars. The effect of active galactic nuclei on galaxy growth is profound. By halting star formation through the processes described, galaxies transition from being star-forming systems to passive systems. The color shift of a galaxy from blue to reddish tones signifies this transition. The cessation of star formation in galaxies, referred to as elliptical or red and dead galaxies, is largely attributed to the feedback mechanisms of their active galactic nuclei. Agons influence structural changes as their feedback interacts with the galaxy's central regions. The interconnected growth of a galaxy's supermassive black hole and its stellar mass highlights the regulatory impact of agons. Another critical aspect of galactic feedback lies in the cosmic recycling process, which includes the ejection, cooling, and reaccretion of gas. Gas ejection is a consequence of processes like stellar winds, supernova, explosions, and active galactic nuclei activity. The mechanical energy from supernovae and Aegean jets drives gas out of galaxies, sometimes removing substantial amounts from the galactic center. The removal of this gas contributes to halting the formation of stars due to the lack of available material. Despite being removed from the core of a galaxy, expelled gas undergoes cooling as it interacts with the surrounding medium. This cooling results in the formation of molecular clouds, which may later become reaccreted by the galaxy due to gravitational pull. The refreshing cycle of gas cooling, falling back into the galaxy, and fostering new rounds of star formation forms a mechanism for continuous galactic growth. This process enables galaxies to maintain prolonged activity in their life cycles, despite periods of quiescence or slowdown in star formation. The regulation of star formation depends on the balance between gas ejection and reaccretion. Intense periods of ejection, driven by aggressive feedback events, can stall star formation as the necessary raw materials are unavailable. Conversely, periods of effective reaccretion refuel star formation, creating phases of growth and activity within galaxies. Cosmic recycling ensures the availability of resources for future star formation events, contributing to a galaxy's ability to sustain activity over its lifespan. Feedback loops serve as an important framework for understanding how feedback amplifies or mitigates galactic processes. Positive feedback can enhance star formation through mechanisms like the compression of gas clouds caused by supernova remnants or stellar winds. Regions within galaxies undergoing active star formation may further promote additional star formation via localized interactions. Meanwhile, negative feedback prevents the overproduction of stars and controls gas availability. Negative feedback is often attributed to events such as supernovae and Aegean activity. By heating surrounding gases and limiting their ability to condense, negative feedback establishes a block to continuous and unregulated star formation. This prevents the depletion of galactic gas reserves while promoting periods of balance within the galactic evolution process. Stellar feedback, including contributions from supernovae and stellar winds, works cohesively with Aegean feedback to regulate galaxy dynamics. Both mechanisms are independent but collectively significant in managing gas availability and star formation across different types of galactic systems. Supernova exert influence over individual star-forming regions, while Aegean feedback operates on a larger galactic scale. The continuous interplay between ejection, cooling, and reaccretion cycles within galaxies highlights the need for a dynamic understanding of feedback processes. By ensuring that galaxies neither deplete nor overproduce stars, feedback shapes the enduring functionality and characteristics of galactic systems. The balance achieved enables galaxies to adapt to their changing environments while maintaining their structural integrity over time. Feedback mechanisms, in all their scales and manifestations, serve as regulators of the cosmic ecosystems that shape the universe. Edwin Hubble introduced a classification system for galaxies in 1926, which is famously visualized in the tuning fork diagram. This system categorizes galaxies based on their shapes and remains a fundamental tool in studying galaxy morphology. According to this diagram, galaxies are generally classified into 4 key types. Elliptical galaxies are smooth, featureless collections of stars. They range from being merely spherical to highly elongated shapes. These galaxies are generally older, containing little gas and having low star formation rates. The stars within elliptical galaxies tend to be ancient, and the lack of gases means few new stars form here. Spiral galaxies are distinct because of their flat disks and iconic spiral arms. They have an abundance of gas and dust and support ongoing star formation. Depending on the tightness of their spiral arms, they can be further broken into subcategories such as C, SB, or S. Our very own Milky Way is a prime example of a spiral galaxy. These galaxies also often have central bulges, where older stars are commonly found. Barred spiral galaxies share similarities with regular spirals, but they possess a bar-like structure at their center. The spiral arms typically extend from the ends of this bar. Like regular spirals, they're also classified further into types like SB, SB, or SBC, depending on the looseness of the arm structures relative to the bar. Irregular galaxies, as the name suggests, lack any specific regular structure. Their appearance is often chaotic, and they are rich in gas. These galaxies are actively forming stars, and this activity gives them a dynamic nature. They do not fit into the spiral or elliptical categories, making them more challenging to classify. Over time, the types of galaxies can change due to various internal and external factors. For instance, spiral galaxies may turn into elliptical galaxies, especially after major mergers. Large amounts of gas and dust get consumed, and the spiral structures are erased, leaving a smoother, more uniform shape. Conversely, although rare, an elliptical galaxy might transform into a spiral galaxy if it acquires significant amounts of gas and dust, enabling the formation of new spiral arms. Such transformations showcase how galaxies are not static entities, but are instead dynamic systems influenced by their environments and interactions. Galaxy collisions and gravitational interactions significantly shape the evolution of galaxies. These mergers play an essential role in altering their size, shape, and star formation activities. Depending on the size and outcome, they are generally categorized as major mergers and minor mergers. Major mergers occur when two galaxies of comparable size collide and merge. These events are dramatic, disrupting the original structural features of both galaxies. If the two galaxies involved are spiral galaxies, the collision can lead to the formation of an elliptical galaxy. During these mergers, gas clouds get compressed, leading to bursts of star formation known as starbursts. Newer populations of stars often emerge as a result of this activity. The antennae galaxies are a classic example of a major merger in progress. These two spiral galaxies are in the process of colliding, causing massive star formation and gas cloud interactions. Over billions of years, they will merge fully, creating a singular elliptical galaxy. During major mergers, spiral arms of galaxies are lost due to the chaotic nature of the interaction. Most gases and dust become unorganized, shaping smoother elliptical forms. Minor mergers, on the other hand, involve a smaller galaxy merging with a much larger one. The gravitational impact on the larger galaxy is subtle, but it gains additional gas, stars, and sometimes even dark matter from the smaller galaxy. Minor mergers are a more gradual process and often result in less dramatic changes. These events play a significant role in gradually building galactic mass and adding to stellar populations. The Milky Way is experiencing such minor mergers through its interaction with smaller galaxies like the Sagittarius dwarf galaxy. These interactions add stars and gas to the Milky Way's structure, subtly altering its features. Collisions and major mergers also trigger intense starbursts when the gas clouds of merging galaxies collapse together. These bursts of star formation lead to the rapid creation of new stars, affecting the makeup of the galaxy. Gas funneling to the center of these galaxies during collisions sometimes feeds the central black hole, making it more active. This activity can further contribute to shifts in galaxy properties. Star formation within galaxies varies greatly across cosmic time and is influenced by a wide range of factors. The availability of gas plays the most direct role in star formation. Other influences, such as feedback caused by supernova explosions and activity around supermassive black holes, also affect star production rates. Around 10 billion years ago, during the peak of cosmic star formation, galaxies were abundant in gas, and the rates of star formation were exceptionally high. These galaxies were generally much smaller and more chaotic in appearance compared to galaxies we see today. They frequently pulled in gas from their surroundings, fueling rapid stellar births. This era saw galaxies expanding rapidly as stars formed at record rates due to these conditions. Today, the star formation rate has dropped significantly. The decline in available gas within galaxies is a critical factor for this reduction. Additionally, feedback from supermassive black holes, which can eject or heat nearby gas, further suppresses star formation. Modern galaxies are more mature, and their lower star formation rates reflect the reduced cosmic activity that characterizes the present era. The surrounding environment of a galaxy significantly affects its star formation activity. Isolated galaxies, which exist away from massive galaxy clusters, often show higher levels of star formation. These galaxies can draw gas from their surroundings and remain relatively unaffected by external gravitational forces. Their stable environments allow for consistent star formation over time. Galaxies located within clusters face different challenges for star formation. They are subject to tidal stripping, which removes gas and stars as galaxies interact with the gravitational fields of neighboring galaxies. Additionally, the dense environment of the cluster may cause interactions with hot gases found between galaxies, suppressing their ability to form new stars. Cluster galaxies often exhibit lower rates of star formation as a result of these influences. Specific types of galaxies show distinct patterns in their star formation activity. Spiral galaxies are known for their ongoing star formation, typically concentrated within their spiral arms. These arms contain dense regions of gas and dust, and the compression of these materials leads to the birth of new stars. Elliptical galaxies, which are often formed through major mergers, generally lack significant star formation activity. The absence of gas within these galaxies means that new stars cannot form easily. Their stellar populations are composed of older stars, giving them their characteristic reddish hues. Irregular galaxies demonstrate considerable variability in their star formation histories. Due to their undefined structures, they may undergo intense bursts of star formation triggered by interactions or collisions with other galaxies. These bursts can lead to unusually high rates of star production and make their evolutionary paths diverse and unpredictable. The study of galaxies reveals a dynamic interplay of factors that influence their evolution. Over time, galaxies have shifted from the chaotic star-forming entities of the early universe to the more stable structures found today. Galaxy interactions, environmental conditions, and the availability of materials like gas are all components of their ongoing transformations. The universe, when viewed on the grandest scales, exhibits a dazzling and intricate structure often referred to as the cosmic web. This interconnected network of filaments, clusters, and voids forms the framework of the cosmos. The cosmic web provides a visual understanding of how matter is distributed across the universe. It emerges from the smallest quantum fluctuations in the early universe, minute disturbances that expanded and evolved over billions of years. This growth and arrangement of matter are shaped by gravity, driving galaxies and diffuse matter to coalesce into distinctive forms. The formation of the cosmic web stems from the distribution of matter after the initial expansion of the universe. During the early stages of the universe's existence, tiny perturbations in the density of matter set the stage for structural formation. These initial fluctuations were minuscule in scale, but over time, gravitational forces amplified them. Regions with slightly higher densities began pulling in more matter, growing larger and denser as time progressed. At the same time, regions with lower densities expanded, pushing matter away and creating vast, empty regions now known as voids. The filaments of the cosmic web are key features in this large-scale structure. These elongated thread-like formations consist of interconnected galaxies, dark matter, and intergalactic gas, spanning vast distances across the universe. They link galaxy clusters together, forming the skeleton of the cosmic web. At the intersections of these filaments are densified regions, often hosting massive clusters of galaxies. These clusters act as cosmic nodes, with the filaments behaving like connective tissue between them. Galaxy formation and evolution tie closely to these filaments. Galaxies are not evenly distributed throughout the universe. Instead, they align along the structures of the cosmic web. Being part of these filaments influences their development in distinct ways. Dense environments found along filaments encourage interactions between galaxies, including mergers and close encounters. These interactions can affect star formation, the growth of central black holes, and even the overall shape of a galaxy. On the other hand, galaxies within voids, far removed from such interactions, often follow different evolutionary paths. Observational evidence solidifies our understanding of the cosmic web structure. Over the past few decades, technological advancements in telescopes and surveys have enabled astronomers to map the distribution of galaxies with remarkable detail. Projects like the Sloan Digital Sky Survey, a comprehensive effort to map the universe, have provided invaluable insights. By charting the positions of millions of galaxies, these surveys have revealed the interconnected filaments and nodes, alongside the vast, empty voids that make up the cosmic web. The significance of these voids cannot be overstated, as they offer a sharp contrast to the densely packed clusters and filaments. These regions, often tens to hundreds of millions of light-years across, are some of the most barren expanses in the universe. However, they are not entirely empty. They contain low-density intergalactic gas and potentially dark matter, but lack the rich distribution of galaxies seen in other regions. Understanding voids is crucial for cosmology, as they act as testbeds for theories about the universe's expansion, dark energy, and the role of gravity on large scales. Voids also provide key observational advantages. Due to their low-density nature, they offer clearer views of distant background objects, enabling astronomers to study phenomena that might otherwise be obscured. Furthermore, their stark contrast with the densely packed regions of the cosmic web illustrates the complementary dynamics of cosmic evolution. While filaments concentrate matter, voids distribute it outward. The concept of dark matter is essential to the understanding of the cosmic web. While ordinary matter, such as stars and galaxies, is the most visible component of the cosmos, dark matter constitutes the majority of the universe's mass. It does not emit, absorb, or reflect light, making it virtually invisible. However, its gravitational effects are profound. Dark matter serves as the scaffolding upon which the cosmic web is built. The distribution of dark matter governs the arrangement of galaxies, and it is intricately woven into the web's filaments and nodes. Simulations have played a significant role in studying the cosmic web. Large-scale computational models, based on theoretical understanding and observational data, help scientists visualize and predict its growth. These simulations start with initial conditions resembling the early universe, incorporating factors like gravity, the behavior of dark matter, and the influence of gas dynamics. Over time, these models show how matter aggregates into filaments, clusters, and voids, providing a detailed view of the cosmic web's structure. The insights gained from these simulations align with observational studies, reinforcing our understanding of cosmic evolution. For instance, computer models accurately reproduce the filamentary structure observed in galaxy surveys, offering clues about the interplay between dark matter and baryonic matter, the ordinary matter composed of protons, neutrons, and electrons. These models also help us understand the role of feedback processes, such as the influence of supermassive black holes in shaping the growth of galaxies within the cosmic web. Additionally, the cosmic web is not static. Just as the universe expands, so too does the web evolve. Over billions of years, the filaments grow longer and denser as galaxies and dark matter continue to accumulate due to gravitational attraction. Meanwhile, voids expand, pushing matter toward the filaments and clusters. This ongoing process underscores the dynamic nature of the universe and its structures. Another fascinating aspect of the cosmic web is its role in shaping intergalactic gas. Between galaxies lies a vast reservoir of gaseous material known as the intergalactic medium. This gas is not distributed randomly, but follows the structure of the web, concentrating along filaments and nodes. Studies of this gas, particularly through its absorption and emission of light, provide additional insights into the cosmic web's properties. For example, the distribution and temperature of intergalactic gas reveal information about the web's evolution and the impact of processes such as galaxy formation and feedback from black holes. The study of the cosmic web extends beyond understanding the universe's structure. It also informs broader topics in cosmology. By examining the distribution of galaxies and voids, scientists can test theories about dark energy, the mysterious force driving the universe's accelerated expansion. Additionally, the cosmic web serves as a natural laboratory for exploring the interplay between baryonic and dark matter, gravitational forces, and the behavior of gas on cosmic scales. Overall, the cosmic web represents one of the most profound discoveries in modern astrophysics. Its intricate network of filaments, clusters, and voids captures the essence of the universe's structure on the grandest scales. From its formation in the early universe to its dynamic evolution over billions of years, the cosmic web offers a vivid picture of how matter organizes itself under the influence of gravity. Observational evidence, simulations, and theoretical studies continue to shed light on this remarkable cosmic tapestry, deepening our understanding of the universe and its underlying principles. Over the course of millions of years, these smaller pieces merge together, forming the skeletal framework of the Milky Way. Evidence of these mergers can be seen in different components of the Milky Way. One of the most significant examples is the existence of stellar populations with ages that vary greatly. The stars in the halo of the Milky Way, which is the outermost part, are some of the oldest stars in the galaxy. They are thought to have formed during the early stages of the galaxy's development. This contrasts with the stars in the disk and bulge of the galaxy, which are younger. Their formation is believed to have taken place billions of years after the galaxy's initial formation. This distribution of stars helps scientists piece together the story of the galaxy's growth. Additionally, streams of stars have been discovered orbiting the Milky Way. These streams are thought to be remnants of smaller galaxies that were torn apart and assimilated by the Milky Way. Over time, these mergers added mass and star populations to the larger galaxy. By tracking these streams, astrophysicists can reconstruct the timeline of these interactions. This gives a clearer picture of how the galaxy evolved from small components into the colossal spiral structure visible today. Another crucial element of the Milky Way's development is the role of gas in star formation. Gas plays an essential role in fostering the birth of stars within the galaxy. The availability of gas leads to the collapse of dense regions under gravitational forces, ultimately resulting in new stars. Different regions of the galaxy have varying concentrations of gas, impacting star formation activity. For example, the dense spiral arms of the Milky Way have a robust supply of gas, which supports ongoing star formation. Moving on to the Andromeda Galaxy, which is also known as Messier 31, and its peers in the local group, we find a wealth of insights into galaxy interactions, and their impact on evolution. The local group is a collection of more than 50 galaxies, of which the Andromeda Galaxy and the Milky Way are the most massive members. Andromeda is also a spiral galaxy, and its structure bears resemblance to the Milky Way, yet it offers unique points of comparison. One of the important aspects of the Andromeda Galaxy is its impending interaction with the Milky Way. Both galaxies are on a collision course due to mutual gravitational attraction. Such interactions can influence the structural and dynamic properties of galaxies significantly. Over billions of years, these interactions may result in the formation of a new galaxy from the merger. This idea is supported by simulations that predict how the gravitational pull and orbital motion of galaxies can alter their structures, leading to transformations such as the formation of new spiral arms or the triggering of intense star formation. Another exciting area of study involves satellite galaxies in the local group. These smaller galaxies orbit larger ones like Andromeda or the Milky Way. Interactions among these satellites and their host galaxies provide additional insights into galactic evolution. For instance, tidal forces exerted by the massive central galaxy can strip gas and stars from the smaller galaxies, a process called tidal stripping. The resulting streams of material often integrate into the larger galaxy, much like the accretion process observed with the Milky Way. Observing tidal stripping in action allows researchers to understand how larger galaxies grow at the expense of smaller ones. High-resolution observations of stars and gas in the Andromeda Galaxy have also revealed patterns of star-forming regions, gas dynamics, and stellar distribution. These studies shed light on how interactions with neighboring galaxies, including the Milky Way, may impact its future. Likewise, the presence of older stellar populations in Andromeda points to a formation history shaped by mechanisms that are quite similar to those seen in the Milky Way. One of the key findings from observing distant galaxies is their structural diversity. Unlike the well-ordered shapes of nearby galaxies, such as spirals or ellipticals, many distant galaxies appear clumpy and irregular. This suggests that galaxy formation in the early universe was a chaotic process marked by collisions, mergers, and turbulent gas flows. Observing these irregular shapes helps scientists understand the role of environment and interaction in the early stages of galaxy assembly. High redshift observations have also allowed researchers to detect intense bursts of star formation in young galaxies. These galaxies, often referred to as starburst galaxies, produce new stars at a much faster rate than seen in the Milky Way. The light emitted from these bursts plays a significant role in shaping the interstellar medium, as stars expel material into their surroundings, enriching their environments with heavier elements produced through nuclear fusion. The study of high redshift galaxies also highlights the importance of dark matter in galaxy formation. Dark matter is an enigmatic form of matter that interacts with regular matter primarily through gravity. By observing how galaxies move and cluster together in the early universe, scientists can infer the impact of dark matter halos. These halos are thought to provide the gravitational scaffolding onto which gas and stars assemble, forming the galaxies we observe today. Additionally, examining the light from distant galaxies has allowed astronomers to measure their redshifts, which indicate how fast they are moving away from us. This movement correlates with the expansion of the universe. By studying the redshifts of numerous galaxies, astrophysicists have been able to map the rate at which the universe has expanded over billions of years. This information has profound implications for cosmology, offering deeper insights into the early stages of space and time. Through observations made possible by advanced telescopes, scientists are also studying the chemical composition of distant galaxies. This allows them to determine the relative abundance of elements, which provides clues about their star formation history. Distant galaxies often show lower metallicity levels, meaning they contain fewer elements heavier than helium compared to nearby galaxies like the Milky Way. This reflects their earlier stage of cosmic evolution, as heavy elements are primarily formed in the fusion processes inside stars. By bringing together observations of nearby galaxies, like the Milky Way and Andromeda, with studies of high redshift galaxies, researchers are creating more comprehensive narratives about the universe's history. The detailed examination of stellar populations, gas dynamics, and structural transformations paints a vivid picture of how galaxies form, grow, and change over billions of years. Dark matter is one of the most intriguing aspects of modern astrophysics, acting as a hidden framework within the universe. Unlike ordinary matter, which is made up of atoms, dark matter neither emits nor absorbs light. It remains invisible to our telescopes, yet it is estimated to constitute about 85% of the total matter in the universe. The primary way scientists detect its presence is through its gravitational effects on visible matter. The first significant evidence of dark matter comes from the rotation curves of galaxies. According to our understanding of physics, stars at the outer edges of a galaxy should orbit more slowly than those near the center, where visible mass is concentrated. However, observations show that stars at the outskirts of galaxies orbit at unexpectedly high speeds. This discrepancy suggests the presence of an invisible mass, dark matter, providing additional gravitational pull. Another key piece of evidence is gravitational lensing. This phenomenon, occurs when light from distant stars or galaxies bends while passing near a massive object. The lensing effect observed around galaxy clusters indicates there is far more mass present than what we can directly see. Additionally, cosmic microwave background radiation, the faint afterglow from the early universe, shows small fluctuations that align with the gravitational influence of dark matter. Dark matter does not exist in isolation. Rather, it forms dense structures called halos. These halos begin forming in the early universe due to primordial density fluctuations. During the inflationary period, tiny variations in density served as the seeds around which dark matter clumped. These initial regions of slightly higher density attracted more matter over time, leading to the formation of halos. The timeline of dark matter halo formation is fascinating. Smaller halos formed first, and later merged to create larger structures. This hierarchical process occurred over billions of years, gradually shaping the large-scale structure of the universe. At the centers of these halos, where gravitational effects are strongest, dark matter acts as a well into which ordinary matter, or baryonic matter, falls. Once baryonic matter is drawn into these dark matter wells, it begins to accumulate and form high-density regions. Within these dense areas, stars are born and galaxies take shape. Dark matter also plays a critical role in linking galaxies together, forming clusters and superclusters that create a sort of cosmic web across the universe. This network is extensively studied using simulations like Illustries and the Millennium Run, which show how dark matter underpins the universe's structure. Dark matter comes with a range of properties that affect galaxy formation. Scientists classify it as cold, warm, or hot dark matter, depending on the speed of its particles. Cold dark matter, CDM, consists of slow-moving particles, making it conducive to the formation of small-scale structures like individual galaxies. Observations favor CDM over warmer variants, as warm or hot dark matter would suppress the creation of these smaller structures. Another unique property is the non-collisional nature of dark matter. Unlike gas, dark matter does not interact with forces like electromagnetism, meaning it cannot cool or dissipate. This lack of dissipation allows it to maintain its influence over large scales, shaping the universe more broadly than ordinary matter could alone. Additionally, dark matter remains stable and behaves consistently, providing a solid foundation for our understanding of the cosmos. Overall, while the properties of dark matter remain mysterious, its effects on the universe are undeniable. From shaping large-scale structures to facilitating galaxy formation, this invisible mass plays a crucial role in our ongoing quest to understand the mysteries of our vast universe. As scientists continue to study this elusive substance through observations and simulations, we may one day uncover its true nature and unlock even more secrets about the universe we call home. So keep looking up at the night sky with wonder and curiosity, for who knows what other hidden wonders await us beyond what we can see with our eyes alone. Dark matter began influencing the universe long before normal matter could. Before the Epoch of Recombination, approximately 380,000 years after the Big Bang, dark matter was already clumping into halos, while baryonic matter remained coupled to photons in a state of plasma. Once recombination occurred and photons decoupled from matter, baryonic material started falling into dark matter halos, setting the stage for galaxy formation. Later, during the period of reionization, around 500 million years after the Big Bang, dark matter acted as gravitational anchors, helping ordinary matter cool and condense into the first stars and galaxies. Modern observations provide compelling evidence for dark matter's role in shaping galaxies and clusters. Galaxy rotation curves continue to show that visible mass alone cannot explain the motion of stars in galaxies. Gravitational lensing remains a critical tool, with detailed observations revealing far more mass in galaxy clusters than their visible components can account for. Large-scale structures observed in the universe also align with the predictions of dark matter models, where the spatial distribution of galaxies follows an underlying framework of dark matter. One particularly striking observation is the bullet cluster, a pair of colliding galaxy clusters. The visible gas from these clusters interacts and slows down during the collision, while the dark matter, detectable through gravitational lensing, keeps moving forward unimpeded. This separation between visible and invisible matter offers direct evidence of the existence of dark matter. In addition to its gravitational pull, dark matter also has other unique properties that make it essential to the formation and evolution of the universe. One such property is its non-collisional nature, meaning it does not interact with forces like electromagnetism. This allows dark matter to maintain its influence on large scales, shaping the distribution of matter throughout the cosmos. Furthermore, dark matter remains stable over time, providing a consistent framework for our understanding of the universe. Simulations are invaluable for understanding how dark matter galaxy formation. Models like EAGLE and Illustries incorporate dark matter to replicate the evolution of the universe from its earliest stages to the present. These simulations reproduce observed features such as galaxy clustering, cosmic filaments, and dark matter halo properties. Insights from these models have deepened our understanding of how dark matter affects star formation, energy feedback, and the shapes of galaxies. Dark matter also shapes the cosmic web, a network of filaments and voids spanning the universe. Within this framework, dark matter halos serve as connecting points where galaxy clusters form. The filaments themselves are filled with both dark and baryonic matter, creating structures that link various parts of the universe. Voids, on the other hand, correspond to regions with low dark matter density and few galaxies. Despite the vast knowledge gained about dark matter, many questions remain unanswered. Scientists still do not know what dark matter is made of. Hypothetical particles like WIMPs, weakly interacting massive particles, axions, and sterile neutrinos are leading candidates. However, despite extensive experiments such as LUX and XENO-N1T, direct detection efforts have yet to succeed. Researchers are also exploring whether dark matter interacts with itself or other forces beyond gravity. Alternative theories, like modified Newtonian dynamics, attempt to explain galactic behaviors traditionally attributed to dark matter. While modified Newtonian dynamics provides explanations for specific phenomena, it struggles to account for the full range of observations explained by dark matter, such as the bullet cluster or gravitational lensing effects. The story of dark matter continues to evolve. It may not reveal itself easily, but its influence is undeniable, shaping galaxies and guiding the universe's evolution. Scientists remain committed to unlocking its secrets, knowing that solving its mystery could redefine our understanding of the cosmos. Modern theories and simulations in astrophysics have revolutionized our understanding of the universe. The development of advanced computational simulations, such as the Illustries project, and the EAGLE project has opened new avenues for exploring the mechanisms behind galaxy formation and evolution. These simulations have the ability to replicate the physical processes of the universe with remarkable precision, giving researchers invaluable insights into various cosmological phenomena. The Illustries project is one of the most expansive computational simulations designed to mimic the large-scale structure of the universe. It harnesses massive amounts of computational power to simulate the formation of galaxies over cosmic time. By incorporating data on gravitational forces, gas dynamics, and dark matter distribution, the Illustries simulation successfully recreated the universe's structure from vast cosmic voids to dense galactic clusters. Through these simulations, researchers were able to closely study how galaxies emerged from primordial gas clouds and evolved into the complex structures observed today. The project provided information about star formation rates in galaxies, the impact of black holes on their host galaxies, and the distribution of heavy elements across cosmic scales. This level of detail was previously unattainable, showing the immense potential of advanced simulations in decoding the universe's history. On the other hand, the EAGLE project, which stands for Evolution and Assembly of Galaxies and Their Environments, also plays a crucial role in enhancing our comprehension of galaxy evolution. This simulation emphasizes the formation and growth of galaxies within a cosmological volume while accounting for complex physical processes like gas cooling and heating, feedback from star formation, and supermassive black holes. EAGLE successfully matches observed galaxy properties such as stellar mass, star formation rates, and morphology distribution. The insights gained from this project helped researchers understand why large elliptical galaxies tend to form in denser regions of the universe, whereas disk-shaped galaxies, like the Milky Way, are more common in less crowded regions. Both Illustries and EAGLE shed light on the interplay between ordinary matter, known as baryonic matter, and dark matter, which constitutes the majority of the universe's mass. These simulations show how dark matter forms the scaffolding upon which galaxies form, grow, and interact with one another. Without the underlying distribution of dark matter, the complex web of galaxies and galactic clusters we observe in the universe would not exist. Understanding this cosmic dance between dark matter and baryonic matter has been one of the greatest successes of modern computational simulations. The role of feedback mechanisms in galaxy formation is a recurring theme in many simulations. Feedback refers to the process by which energy from stars, supernova, and black holes regulates the temperature and motion of surrounding gas. Both the Illustries and EAGLE projects reinforce the idea that feedback processes play a pivotal role in determining the size, shape, and composition of galaxies. For instance, intense gas outflows driven by supermassive black holes can heat surrounding gas, preventing it from cooling and forming new stars. This explains why some massive galaxies transition from actively forming stars to becoming passive, quiescent objects. Despite their advancements, simulations like Illustries and EAGLE also emphasize the gaps in our understanding. While these models can reproduce many aspects of the observed universe, discrepancies remain. For example, accurately predicting the abundance of small satellite galaxies around larger systems, like the Milky Way, has been a persistent challenge. Additionally, the interplay between small-scale processes, such as individual star formation, and large-scale processes, such as the dynamics of galaxy clusters, requires further refinement. The next frontier for modern simulations lies in addressing these unresolved questions with the help of new observatories and advanced computational technologies. Observatories, like the James Webb Space Telescope, bring unprecedented observational capabilities, allowing researchers to study faint and distant galaxies in unparalleled detail. These observations serve as benchmarks for refining simulations, enabling models to closely align with real-world data. Beyond observational support, advancements in computational power will continue to drive progress in cosmological simulations. With stronger supercomputers, scientists can simulate larger cosmic volumes at higher resolutions, capturing even the minutest physical processes. Incorporating additional forces, such as magnetic fields and their influence on galaxy formation, is another area where simulations are expected to evolve. The synthesis of observations, computational simulations, and improved theoretical frameworks has positioned modern astrophysics as an era of tremendous discovery. The collaboration between projects like Illustries and EAGLE and observational data from upcoming observatories will bridge remaining gaps, bringing humanity closer to unraveling some of the most profound mysteries of the cosmos. Through an iterative process of testing and refinement, these tools will continue to guide our exploration of how galaxies form, evolve, and shape the universe. Each step forward reveals not just the grandeur of the cosmos, but also the ingenuity of human curiosity in understanding its intricacies. As we journey through the universe's vastness, it becomes clear that gas plays a central role in shaping galaxies. From the primordial clouds that birthed the first stars to the intricate feedback processes that regulate galaxy growth, gas is the lifeblood of cosmic evolution. It fuels the formation of stars, drives the dynamics of galaxies, and determines their fate. While we continue to uncover the mysteries of dark matter, black holes, and cosmic expansion, the humble gas remains a constant force, shaping the universe in ways we are still striving to fully understand. The cosmic story is far from over.